Okay, this is 12.7 notes, applications of exponential in logarithms. So first we're going to look at the applications of exponentials, and by doing so, we're going to look at 4 equations. We're going to look at compound interest, compound continuously, double life, and half-life. Okay. So what you'll notice on each of these, a lot of the variables are the same. So A stands for the amount. This is the amount that you're trying to achieve. Okay. Then P stands for the initial amount or the principal, so the amount of money or whatever that you have. Okay. Then we have R, which is the rate. And what's important here is that the rate is always a decimal. So I'm going to write that here. Rate is always a decimal, and that is for every single one, every time you see rate. N stands for the total number of times per year, and T stands for total years. Okay. When we get to double life and half-life, the only differences is double life has D, which is doubling time. They will give you this in the problem. And then half-life has H, which is half-life time. And again, they will give you that in the problem. So looking at example 1, says your account has $500 and an interest rate of 6% compounded yearly. How much is in the account after 3 years? Well, this is going to be the interest formula. And remember, that is A is equal to P times 1 plus rate divided by number of times per year to the power of number of times per year times total years. So this is going to be equal to 500 times 1 plus 0.06 over 1, because compounded yearly, that's the amount of times per year, to the power of 1 times 3. You're going to type this into your calculator exactly as is, and you're going to get the amount 595.51. So $595.51. Number 2 says you invest $100,000 in an account with 1.01% interest, compounded quarterly. How much will you have in 25 years? So this is also an interest, so that's A is equal to P times 1 plus R divided by N to the power of NT. So we have 100,000 times 1 plus our rate. And notice that even though this looks like a decimal, it's actually a percentage. So I would change that by moving 2 decimal places to the left. So this is 0.0101 divided by 4. Quarterly represents our N, 4 times a year, to the power of 4 times 25. And if you type that into your calculator, you get $128,683. Okay, number 3 says your computer costs $1,500, but it depreciates in value by 18% each year. How much will your computer be worth in 6 years? So we're still using that interest formula. The A is equal to P times 1 plus R over N to the power of NT. So $1,500 is our initial value, how much you paid for your computer. But since it says it depreciates, we're going to make sure that our rate value is a negative. So this is going to be 1 plus negative 0.18. And then each year, so that's the number of times it depreciates. So 1 to the power of 1 times 6, the total amount of years. So you would plug that into your calculator and you would get $456.01. Number 4 says the half-life, so that is telling us right there what equation we're using, of a medication is the time it takes the drug to be eliminated from the body. The half-life is 2 hours. If your initial dose is 200 milligrams, how much Advil is left in your body 6 hours later? So this is A is equal to P times 1/2 to the power of t divided by h. So we have 200 times 1/2. T is the total time, 6 hours, divided by the half-life time, which is 2 hours. So we get, if we plug this into our calculator, 25 milligrams. Number 5 says, if $8,000 is invested in an account that pays 4% interest compounded continuously, how much is in the account at the end of the 10 years? So since it says compounded continuously, we are using the formula A is equal to P times E to the power of RT. So we have 8,000 times E to the power of our rate, which is 0.04, times our total time, which is 10. Put that in the calculator, and we get 11,934.60. Okay. So that concludes the applications for exponential. This next problem is an application for logarithm. So it says the Richter scale is one way of converting seismographic readings into numbers that provide an easy reference for measuring the magnitude of an earthquake. All earthquakes are compared to a zero-level earthquake whose seismographic readings measure 0.001 millimeters at a distance of 100 kilometers from the epicenter. An earthquake whose seismographic readings measures X millimeters has a magnitude given by this formula. So this is the formula we're going to use, where X naught is equal to 10 to the negative 3 power. It says find the magnitude of each earthquake that follows. So starting with part A, it says Mexico City in 1985 has a seismographic reading of 125,892 millimeters. So we use our equation, m of x is equal to log of x divided by x naught. What they gave us here is x. So this is equal to log of 125,892 divided by x naught, which is what they gave us over here, so 10 to the negative 3rd power. You would plug that into your calculator and you get 8.1. Same with the next one. It says San Francisco in 1906 had a seismographic reading of 50,119 millimeters. So we would plug in that value for x, so 50,119 over x naught, which is still 10 to the negative 3rd power. We would plug this entire thing into our calculator and we would get 7.7. So if we're looking at both of these earthquakes, remember that a Richter scale, the larger the number, the more destructive the earthquake. So if we're comparing the two earthquakes in 1985 and 1906, the Mexico City one had the most destruction since it was an 8.1 on the Richter scale.